Hi there guys, in this video we're going to have a look at what we call the normal approximation to a binomial distribution. Right, so if you look at this diagram down below here, what I've got is the discrete random variable x. And I know it's a discrete variable because I'm telling you here on the left here, x is distributed binomially, and the parameters we're looking at are the sample size and the probability. Now if we were to plot these probabilities for different values of x, sometimes, and only sometimes, it may look like this. And the reason I've drawn these single lines is to represent that these are discrete values. Remember, for the binomial distribution we're only using discrete values, and therefore there is nothing that exists in between these lines. It's just these are the different values. For example, like shoe size, if this was a size 7, that would be an 8. You can't have a 7.9, for example. I know you can have half sizes, so you could have 7, 7.5, and then 8, but they would have their own line. Okay, so they're still discrete values. So, what I'm going to show you now is a little tool, but what you'll see is these bars will actually touch, because what they're doing, they're not showing you the actual value, they're putting a little bar around it like so, okay, and that's what you're seeing. So when you see these bars, it's actually the middle of the bar that we're going to be looking at. So let's just, hopefully this loads. Okay, right, so I'm just going to yeah, okay, perfect. Right, so up here what I can do is I can drag the sample size, okay, so I can go anywhere between 0 and 50. Unfortunately I can't go further than that. And here I can change the probability. Okay, so these bars, you can see here in the middle it says 7, so 7 should be really a straight line, but just so you can appreciate what I'm trying to tell you, the bars are really useful. So what I want you to look at is if I go right up to 50 and I take this up to 0.5 roughly, that's not a really good one actually. That's a good one, right? So 0.5 to really close to 0.5. You should be able to make a observation about this, and hopefully is the fact that it's quite symmetrical. It looks symmetrical. It looks like it's following a normal distribution curve. So that's interesting to us, because if it looks like it follows it, we can use it to model it. Now, if we take the sample size all the way down to like something small, you can see that symmetry is gone. And I can actually put the normal approximation curve on there. Okay, so you can see it's not a great fit. If I take it back up to 50, you can see, wow, it's hitting the values pretty much every single time there. So if we drop it down to say 30, let's see what that looks like. So it's not too bad if you're comparing the middle of the bars. Yeah, it's still looking like a pretty good fit, even though these bar heights aren't as symmetrical as they were. And if we take the probability down, let's take it down there, you can see it's slightly missing, but it's not bad. Okay, so what we noticed, in certain circumstances we can use a normal distribution to approximate values for a binomial distribution. And that seems a bit strange because one's discrete and one's continuous, but we'll talk more about that in a minute. So what are these special conditions? Now, in the book, they will tell you, number one, oh, that didn't work, try again. Number one, when the sample size is large, and number two, when the probability is close to 0.5. So you saw there, I could only take that up to 50. In the book, when you have questions on this and in your exam, you'll probably have sample size of like 150, maybe even 200. And we're looking for a probability that is close to 0.5. It has to have both of those for it to be considered a good option to use a normal approximation. If it's neither of those, then we shouldn't be using it. We should just be working out binomially as normal. Now there is another condition, which is NP, so the sample size times the probability is greater than 5. And NQ, Q being 1 minus P, the probability of not being successful, so N times probability of not successful is also greater than 5. Now if these two conditions are met, then it also is a good well, it's acceptable to use the normal approximation. But the book don't tell you that, which I find interesting, but you will see it on mark schemes, so it's good to know. Right, but before we go any further, it's important to understand that discrete values can never be distributed normally, because a normal distribution is continuous and a binomial distribution is discrete. But under those special circumstances that we just spoke about, it resembles it really closely and it can be used as a good approximation. And we're going to look at, in a little, towards the end of the video, how good of approximation that is. So, two things you need to know, and you need to know these off by heart, is that the mean is equal to the sample size times the probability. And that surely makes sense. If we think about rolling a 6 on a dice, the probability is 1/6. So if I said to you, on average, the mean, how many 6s would you expect from 36 rolls? Well, you'd say 36 sample size times the probability, wouldn't you? And you say, I'd expect 6. So that one you shouldn't have to really remember, it's just obvious. But this next one, maybe not so. Now the square root is the sample size times the probability of success times the probability of not being successful. So these two things are the same, and you square root it. You need to know that, remember that as we go through this video. Right, so I've put some numbers on it this time. So you've got to be careful here. So x is distributed binomially with a sample size and probability which we don't know. Okay. Now you'll notice here I've got a y. It was an x. As soon as I'm changing it to a normal, I want you to change the random variable, and you'll see some questions when they do that for you as well. And that just shows me that we're now changing distributions and that variables should change. That's good practice. And these are the parameters for a normal. And to work these out, you can use the binomial, so np and square root of npq, right? So that's how they're going to link. So this is one of those circumstances where the discrete variables look very closely to a normal distribution, so we can use it to approximate. And that is something called a continuity correction. Right, so what I will say is, I said it earlier, but I'll just say it again. So because this is discrete and there's loads of space in between these, and these are just observed values that we've got up here, we're going to draw boxes 1 unit wide. The reason it's 1 unit because these are 1 unit, okay? But it's always going to be the case. Something like this, okay? Here's one I made earlier. Now, this is all well and good, but you can see that under here there's space not included, and we've got space outside as well that is being included if we take the boxes into consideration. So that is why we had to do this continuity correction, just to, and it'll all become clear soon enough. Right, so let's have a look at this. So if we wanted to work out the probability that our random variable is less than 28, well, we can approximate it. That's why I've changed my equals to a squiggles using the normal distribution. Now to do that, what we're always going to do is draw a picture. Now we're looking at 28. Okay, so there's my discrete line representing 28. Now if I draw my box around it, just like I have over there, I'll always draw this every single time. We've got our line goes through the box and up in that direction. Yeah, that red line, I'm just drawing this box again over here. Now what we actually want is all the values less than 28. So this is 28, this is y. We actually want everything less than 28. And I'll show you an example in a minute when we go into this box, but we just want it there, less than 28. So that is the same as saying less than, well, what is this value? Because the next discrete line would be 27, so in between here we have 27.5. So if we knew these parameters, we could now use our calculator to work out that, and working out this is an approximation for working out that. Here's another one. So we're looking at less than or equal to 32. So that is approximately equal to, using the normal distribution. So let's draw a picture. So y, we've got our discrete line at 32. I'm going to draw a box around my 32, so we're just imagining this box. What's the line do on 32? Well, it's over this side, so you can see it's coming down here. And what do we want? We want less than or equal to 32. So we definitely want this area less than 32, all of this to the side, but we also want it to include 32. And when that happens, we go into the box, but to the other side of the box. Okay, so once you go in the box, you don't stop halfway, you go all the way across. So this is the same as working out this. We can't do it because we don't have any of the parameters. This is called the continuity correction. Okay, this is a slightly different one. So we're going to exactly the same approach. So we've got 29. We're going to draw a box around it. 29 is on the left of the mean, so we can see it going like this. But this time we only want this one point in the distribution. Okay, so what we actually want is all of this, okay, this whole box that represents 29. So to do this, we're going to say it's the same as this upper bound, take away this lower bound, the whole entire box. So we're going to go to 29.5 to 28.5. Okay, that's the continuity correction to solve this problem. What I didn't say earlier is, you notice I didn't put the equal to sign, so I just flip back to the last one if you're wondering what just happened. And that's because on continuous we don't, and it all comes back down to the 0.9 recurring equals 1 problem. We mentioned it right at the start of this journey on normal distribution, so I'm not going to say any more about it now, but you know, ask me on Teams or whatever. Okay, one more, and then we're going to start looking at some proper questions with these parameters. So what we actually want now is the probability that our discrete random variable is between 27 and 31, inclusive of 31. So actually what we're going to have to do now is draw two boxes. Okay, so I'm going to put my y's on here. This time it's 27, and this one is going to be 31. And 27, we can see the line is coming this way. 31 is on the other side, so it comes through that way. We want it more than 27, okay, so we want this bit here. Do we go in the box? No, because it's not equal to it. But this one is, so we want less than 31, so we want this side, but also, because it has to include 31, so we include in the box, we're going, remember, we don't ever go halfway. Once we go in, we go all the way across. So this is the same as using, remember, you're not going to have the equal to sign, it's continuous. So we're going to go all the way to the other side of 31, 31.5, and 27.5 here. So lots of people get confused with this because they want to take it down and up, or, you know, you just draw the pictures. Don't try, there are ways and patterns that people will tell you. That's not my advice. Just draw the picture, really think about it. Okay, so here's a question with some parameters in here, okay? So earlier on I said you must remember a couple of formulas. So if we've got the binomial distribution, we need to be able to write what these parameters are. And this is the mean, okay? And the mean is equal to NP. So 30 times 0.4, that's 12. Now, the standard deviation is NP cubed. We've already got NP, so if you times it by the probability of not successful, 0.6. And then, remember, we have to square root it as well. So, square root of that. And we get 6 root 5 over 5 squared. Okay, so what I'm going to do is I'm going to store that as a, and I'm just going to put a little a there because that often comes in handy. Right, so we want to work out the probability that x is less than 10. Just to remind you, this is gone, this is the line here, this is the discrete value, this black line here, but here's my blue imaginary box around it to help me understand how I can use a normal distribution for a discrete value. But I'm going to draw a picture of that myself. So here we go. Y, that's 10 There's my box. I'm going to lose my colours now. 10 is on the left side of the mean, so it's coming up here. We want everything less than 10, so we don't want the box, we want it before the box. So this is the same as saying it's approximately equal to the probability for the y variable, the continuous variable, less than 9.5. And now we can do that on our calculators. So menu 7, 2. Now we can put something ridiculously low. I'm just going to go with 0, but you could put like minus 100 if you wanted to. The upper one is 9.5. We have a standard deviation. Well, I stored that as A, so I'm going to put alpha A. It's 2.6832. And my mean was 12. And I get that to equal 0.1757. Okay? We've got a few of these. This video is going to be quite long. So that's the continuity correction. That's one I just prepared earlier, but I didn't actually answer it, so there we go. Now, same thing, but greater than 14. So, 14 is on the right hand side, so my line's coming this way, and we want all the values greater than 14. Right, so we want them all over here. They're not going in the box because it's not inclusive. So this is the same as saying y is greater than 14.5. So let's do that. So menu 7, 2. The lower, this time because we want this part, so we want all of this shaded region in here, I'm going to go 14.5 as my lower and something ridiculous like 1,000 for my upper. My calculator will remember everything I've just put in, so I just press equals, and I get 0.1757 to 4 dp. Equal to 9. So remember when it's just the point, so that's a 9. We want this whole box now. I should draw the line. Doesn't really matter for these ones. Okay, so I want the whole box. So I'm going to go up to 9.5 and down to 8.5. If I want the box, I go the whole box. I never go halfway. So this is the same probability y is less than 9.5 and more than 8.5. Let's grab our calculators. Menu 7, 2. So we've got a lower, 8.5. We've got an upper, 9.5. And the calculator should remember everything else. It's a horrible colour. And 0.0797 to 4 dp. So why not have a go? You've listened to a lot, so pause the video, have a go for this one. And when you're ready, just press play, and I hope you get it right. So, big section, so we're going to have to draw 2 bars. So here's my 2 lines. I've got one at 10, one at 15. My imaginary box around those discrete values. 10 is to the left of the mean, the line's going through this way. 15 is to the right of the mean, it's coming through here. I want it greater than 10, so we're looking at this side, not the box. I want it less than or inclusive of 15, so I want less than 15, but I also want including 15, so I enter the box and I go all the way through the box. So this is the same as saying up to 15.5 and as low as 10.5. So this is what we call a continuity correction to solve this problem. Okay, you can't just use the same numbers. Let's just do it. Okay, so menu 7, 2, we've got 10.5 up to 15.5. Okay, so that is 0.6159. So here we have some more exam style questions here. Okay, so we've got everything we needed to. You can see, just to reiterate the point, large sample, probability close to 0.5. On some of the ones earlier I had was a sample of 30 and a 0.4, so that kind of doesn't obey any of those rules. Just show you that quickly here. But when you did NP, that's greater than 5, and NQ is greater than 5, so that's why it works. So use this to solve this problem. Right, so normal distribution curve, y, this is what we have. We have 72 there. The question is solve the discrete value of less than or equal to 70. Okay, so if I now draw my discrete value at 70, my imaginary box around it that is there. The line coming through my imaginary box will be going in this direction, and I want everything less than 70, but I also want it to include 70. So I go into the box and I go all the way across the box. So the probability that the random variable, the discrete random variable, sorry I should have said 70, is approximately equal to the continuous random variable is less than, we don't include the equal to because it's continuous, 70.5. So we can do that. So menu 7, again, same old here. So I'm just going to put 0 as my lower, 70.5 to be my upper. So the standard deviation is 6.12 and the mean is 72. It tells us that in the question. So they don't actually have to tell you this bit. They could have got you to work it out from here. So it's unusual for them to tell you this. And I make that 0.4032. Okay, let's shrink this just to make sure I've got enough room at the bottom. So part B. I'm going to draw this picture out again. There's my y, there's my 72. And this time we're looking at 80 to 90. So we're looking at this end here. So 80 to 90. This is the bit we're interested in here, and I probably should have shaded that bit there. Okay, so probability x, oh, that's wrong. 80 is less than or equal to x, so more than or equal to x and less than 90. Okay, so 2 limits, so 2 sketches. One at 80, one at 90, single line representing my discrete value. Imaginary box around it. On 80 and 90, the line is coming through this way, and I want more than 80, but I also want to include the 80, so I go into the box and all the way to the other side. I want less than 90, but I don't want inclusive, so I don't go in the box. So this is approximately equal to y being less than 89.5, but more than 79.5. Calculators. So 79.5, 89.5, and it should remember the standard deviation in the mean, and that gives me 0.1081. I've got a few more. So I particularly like this question. This is far more realistic to the type of question you could expect to receive. So first of all, there's no mention of random variables, so we're going to have to define one. Now, so here we go. For a particular type of flower bulb, 55% yellow flowers, we have a probability and a sample size of 80. Okay, so let's say it's the number of bulbs. You can see that's a discrete value because it's the number of bulbs. So number of bulbs producing yellow flowers. Excuse the writing. So x is distributed binomially, sample size of 80 and probability of 0.55. Okay, so can we use a normal approximation for this? Yes. Large sample, close to 0.5. NP and NPQ is also greater than 5. This is nice because you can start to appreciate how good it is. We're looking at the percentage error now. That there'll be exactly 50. Okay, so if we use the binomial distribution, when it's a point, we can use the point distribution function on a calculator, but you will lose marks if you don't show how you do it. So we have 80, we're going to choose 50. Probability of success, to how many times we want it to be successful, in this case 50. probability of unsuccessful probability, or Q, or 1 minus P, raised to the, what else we have. And if we work this out, go away. Go away. Sorry about that, I wasn't telling you to go away, that was my son. Delightful. Right, so let me just type that into my calculator. I'm just going to cheat and use the point distribution. So I've got 50 as my x. Oh, I've used the wrong one, like an idiot. So binomial point distribution variable. So 50, n was 80, and probability 0.55. Okay, so that is 0.0365. I'm going to leave it there. But I'm going to store that as A. So store as A. Right, so if we're going to do a normal distribution, this time we're going to call this y. But before we can do that, we have to set the parameters out. So y is distributed normally. So we have to do n times p, 80 times 0.55. And that's 44. So now we know we have a mean of 44. Times that by 0.45, because that's the Q, and square root it. So we get 3 root 55 over 5. That's squared, remember. That's the bit I often forget. Squared. Right, so we want exactly 50. So 50, y, 50, imaginary box. The line's coming through this way, but we want just this one point, so we want the box, so we take both sides of the box. So it's approximately equal to the probability of up to 50.5 and more than 49.5. Let's work this out. Menu 7, 2. You've got your lower, you've got your upper, standard deviation. I'm just going to type that in. I'm going to type this bit in here, okay? So I'm just going to do 0.6 root 55. It's actually a really nice idea to store that in your calculator as well. It's roughly 4.4497, and the mean was 44. Okay. And that gives me an answer of 0.0362 to 4 dp. I'm just going to store that as B. So I'm going to store that as B. Right, so the percentage error. Well, percentage error means, you know, this is the exact one, okay? So that's going on the denominator. So we just want to work out really what the difference is between these two, which is bigger A. So I'm going to do A alpha, so I'm going to do that to take away that. So I'm going to go alpha A minus alpha B. And you get, it's written in standard form, so I'm just going to write A, take away B there. And then I'm going to times that by 100 to make it percentage, so times, so I've got to divide that, first by 0.0365. And then we times that by 100. And that gives me 0.92. That would do. So it's 0.92% out. So it's less than 1% out. So that is why we consider this a useful tool to use. Why we don't just use the binomial, we can use a normal approximation. Okay, guys, you'll be glad to hear that's it. It's a long video. Right, but best of luck. It's a hard task to get your head around at first. Once you get it, it's easy. Where you're going to go wrong, you're going to forget to square root it. That's the place where I go wrong. And you might get confused with your continuity drawings, but draw the picture every time. It's safe. You know, don't be arrogant. Best of luck.